Hello everyone. Hello everyone. Sorry for the echo. Whoops. Okay. Seems to be good now, I hope. Okay. This is an extremely random lesson because I'll try to put all the missing pieces of C# that we didn't learn yet that are not extremely useful for a beginner, but that are quite useful overall to know. And especially if you want to step up your game to raising qualification, show that you understand not only how to write code which works, but you understand what you're doing. This is quite useful to know. So we'll talk about many different things in this lesson. And those things are tuples, deconstruction, discard operator, expression trees, garbage collection, unsafe code, preprocessor directives, calling private method, and creating objects without knowing their type. So a lot of different things, and I don't expect you to understand everything. It's just so you know, so you're familiarized, so you are aware of things that you could do with the language, and there are many things that you can do. And more than the slides, more interesting will be code examples because there are plenty. Let's start from tuples. A tuple has been in C# for a while now. I won't say the exact version, but essentially it is, instead of an array, you can have a data structure which holds a bunch of values, 2 or more values in a shape of properties or fields. A simple tuple is a reference type, and it's a generic data structure which holds as many fields, as many properties as you pass it the generic types. So for example, here I created a tuple which has 2 properties. First property is of type int, second property is of type string, 5 and test. If it prints, it gets printed 5, test in brackets, like this, exactly like this. Tuple is not very convenient by itself. The simple tuple is not very convenient because in order to access its values, you'll also have to write tuple.item1, tuple.item2. It works, but it wasn't very convenient before, and therefore it didn't see much daylight before. However, it changed quite a bit when value tuple was introduced. So value tuple is exactly like tuple, but it's a value type, meaning which it stays on a stack, and it stores everything in fields. And the things that it enables us storing fields into named fields. It allows us to pick our own names for fields, and quite simply, we don't even need to write new. We can just say brackets. In brackets, we can write number. Number is 1, word is test, and then we can access those fields immediately. Quite simple, quite convenient, and you might ask yourself, if I can write something like this as a variable, can I also return it like this? And the answer is yes, you can, and that's called deconstructing. You can return tuple like this. This means I return 2 values from my method, and I actually return a value tuple. And when I get those 2 values, I can either get it to a value tuple or I can deconstruct it. And this, if I don't get this to a value tuple and instead get those 2 values, it's called deconstructing. Instead of getting a value tuple, a single object which holds 2 fields, some number and some text, I can get instantly two variables, a and b, int and string, whatever belong to the tuple. Questions. Is tuple equal to maps in Java? No, it's nothing at all. All right. So it doesn't mean that 5 maps to test. It just means that I have 5 and test separately, and I can access them separately. And here in this example, I returned 5 and test into different variables. So before we knew that we can only ever return a single value from a method, but with a value tuples, it's quite different. We can return multiple values. It's still a value tuple, and this is just deconstruction, but it's an illusion that we can return multiple values. Pretty cool. Let's move on. You can also deconstruct normal classes. By default, of course, you cannot do that, but it is possible. And all you have to do is to define your deconstruct method. And this deconstruct method has only out parameters. And those out parameters means what can you possibly deconstruct into. So I can deconstruct into name, description, and lines count, for example. Here we have an order. Order has a header. Order has a bunch of lines. So header says what order it is, its description. Lines is details about that order, what items and how many. For example, the most important data that we normally want to get from an order is its name, description, and how many items are there. And we can get this by using name equals header.name, description. So this is just setting those out variables. This is not deconstructing. Deconstructing this basically enables the following. It enables this. So now we can return the data. We can deconstruct that data like this. We can, let's say, create an order and get its name, description, and lines count like that without getting an actual order object. We can simply get those 3 variables right away. And that's pretty much true. Sometimes your values are just way too different to be returned by a single different specified dedicated object, and you want to instead use a tuple, something that just holds unrelated values together. Let's continue. With tuples, with deconstructing comes an interesting addition that we haven't talked about, and that's a discard operator. Discard operator is not unique to tuples or deconstruction. It's unique to out parameter and ref parameter. No, not ref parameter, just out parameter, I think. What does that mean? That means that we can say that we don't care what the function returns. We don't care about the last thing it returns. It's as if we just called a method which returns something, but we don't get the result. Because it wouldn't make sense not getting result for something that returns a value in that kind of a function, but it does make sense if we want just one result, because when we have an out, it's usually multiple results that we get. It's usually something that happens, something with side effects. And prime example is try-parse pattern, which returns 2 values. Result, true or false if the parse was successful, and it outs a value, the result of the parse. What if we want to just validate if if the string is datetime, if it's valid? We can simply say datetime try parse with an input and out nothing, out the discard operator. And this will simply ignore the result and return is datetime, but not the actual datetime. Quite useful. Now let's move on to expression trees, a much more complex topic and a much more niche topic. Personally, I'm not very proficient with expression trees, but I've dabbled with it, and there might be cases where you need them, especially if you're in an extremely complex dynamic world. So what are expression trees? Expression trees are essentially a tree data structure which holds code. So you take code that is translated into data, into expressions. And expressions, basically for every piece of code, there is a piece of an expression. So for example, if you want to have an expression tree for, let's say, a factorial calculation, you can literally put the whole function and its body into expression trees, into expressions, have it under a single expression tree, compile it into a Lambda expression, and execute that as a delegate. Expression trees are quite useful for multiple reasons. But the main reason being is that if we can convert code into data, we can do the opposite. We can convert data into code. So if we can convert expressions, code into expressions, and then expressions back into code, you might ask yourself, isn't that redundant? Not quite. The main point of this is that we can actually convert not to the same language anymore. And the prime example of such conversion is, what if you need LINQ? LINQ is language integrated query. It is like a language of its own. So we can take code, put it in expressions, and have dynamic LINQ using expression trees. So here, let's say we have a simple expression, a parameter that goes to LINQ. So this basically reads, we have parameter of type less than 1 named p1, and we say that we have a Lambda expression, like we're trying to create an expression for Lambda, which takes lesson and returns bool. So it filters lesson. What does it mean? It means that it creates an equality expression which takes parameter 1 and it takes name, and it checks if this name equals less than name equals 13, if parameter.name equals less than 13. So it checks if the lesson that we passed as a parameter, if that lesson's name equals to lesson 13. It wouldn't make sense if you want to convert to different languages. You can use predicates, that's true, but there are sometimes more complex cases. With predicates, you can use and, or, else, and so on. But with expressions, you can use many more things, not just those. And anyways, under the hood, you would need to, if you want to use predicate somewhere else, you would need to do conversion to an expression. I also, when making this example, thought that it does make sense. Oh, in here, predicate. Probably you're correct. I'm not sure about expression semantics. If it accepts predicate, it probably does. So that is correct. Predicate which takes lesson, not lesson bool. And here in this example, the point was that we take, imagine that we had a very similar expression, except that it filtered for, let's say, lesson 1. And here we can combine those two expression bodies into one expression. And the end result would be that we combine them and we compile them into a single expression, and we get a lambda that we can execute or pass into LINQ. So this is how you can combine LINQ. For this specific case, I would agree that just passing predicates and not expression trees. And I understand that it's very difficult to understand. This is very difficult to grasp if you haven't worked with it. And I don't expect this to be understood. Just saying that there is a way of having code in expressions. So another practical example for expression trees is LINQ to SQL. LINQ to SQL, you don't know this yet, but basically we can compile LINQ into SQL, which is executed under the hood as SQL. We can have query syntax, LINQ syntax, doesn't matter. But if we use not IEnumerable, but IQurable, that will be understood as a query that can be converted to SQL. How does that query might look like, you might ask? And I added a link here. And if you look at IQurable, you see this key point here. IQurable is basically an expression, some data structure that holds an expression, and it's convertible to SQL. So another example, again, is when we want to convert something to a different language, expression trees is the way to go. Yeah, I also used the expression. I can show one more example if I can get it quickly. So here is another example. It's not the best example, but it's all right. Basically, if you want to create your own domain language, which has the end result that looks like this. Whoops. That looks like, whoa, that's UI tests, that's repository test. If you want the end result that looks like this, for example, if you want to be able to filter stuff, get stuff like with your domain language filters, like you see you have a filter and you created literally like human language, like title like or title like. So basically it translates into lesson.title equals lesson 2 or lesson title equals lesson 1. Not equals, but contains. You can create your domain language. And this has very complex implementation. I'll just give you a quick look at it. It definitely don't need to understand it. If you want to have a look at it, I'll give you a link. But basically, you have domain-specific queries and then entity framework-specific queries. But you use one or the other, it doesn't matter. It gets converted when you execute it. So you have complete decoupling from entity framework. Again, words that you don't need to understand yet. So we have specifications. And for every specification, for every kind of specification, we have basically an interface. And this is a visitor pattern, if anyone knows design patterns. And it basically means I pass an item and I get a result if it's satisfied by this thing. So it's like a predicate, basically, except it's object-oriented predicate. It's not functional code, but it's object-oriented code. And this basically takes an expression, more like a query, and converts that into an expression. So every specification has its own visitor, which returns an expression that Entity Framework can execute. Complex, I won't explain much. And you can combine different expressions, so you can combine specifications. For domain, it's just an and for entity framework, you'll see it's a bit different. So if we look at infrastructure, how it looks like there, in expressions, you'll see, let's say, lesson expression. Extensions maybe is more interesting. You can see or else expression, that we can combine expressions, invert expressions, and so on. And those now are expressions for entity framework. Not that it's unique, that expression itself is unique to entity framework, but that it will react for entity framework models, as we can see in here. Here, E entities, all those generic types are now entity framework entities. So I basically adapt a domain-specific expression to entity framework expression, and I get the result that I want. Way out of topic, way complex, way more complex than you need to know and understand right now, but it's just another example how expressions can be used. That thing that I just showed you is a specification pattern, which basically you pass a specification into a service and it gets something by that specification, and you can combine specifications in any way you want. You wouldn't possibly be able to do that with just and, or, not symbols, because they are not expressions, they're not pro expressions, they're just simple domain objects. And that's why it's useful, because you basically create your own language that you can make simple, but it takes time to get used to. Now let's move to something more technical, which is alumni's area of expertise, so please correct me if I'm wrong about certain stuff. So you know that when you create variables, when you initialize stuff in your code, it takes memory, obviously. But the problem with memory is that it's not allocated evenly. It doesn't take every bit exactly, and it doesn't get saved compact. It leaves little spaces. It leaves little spaces like this. So when we are creating many things, those spaces expand. There are more and more gaps, and basically memory gets fragmented. Memory fragmentation over time is a thing, and it needs to be fixed somehow by something. And the thing that does this fixing is called garbage collector. Garbage collector exists in managed languages like C# or Java. It doesn't exist in languages like C or C++, and therefore you need to manage the memory there yourself in C or C++. But in C#, we don't really care, because we have garbage collectors, which go and basically cleans up those spots, frees up memory that's allocated, and cleans up those fragmented spots. So it does two things. When we no longer use a referenced object, we can dereference it, we can garbage collect it, in other words. Or when memory is fragmented, like in here, a garbage collection basically compacts that memory and removes those spots. When this garbage collector gets activated, so from MSDN docs, there are 3 conditions when it gets activated. So when you are low on RAM, garbage collector will hit it, will be triggered. There is a certain memory threshold that also is being adjusted based on process lifetime, and it will just be hit eventually by garbage collector. It will trigger when it passes that threshold, and sometimes you can call that method yourself manually, but that is not recommended. So in general, there are 3 simple rules. Avoid calling garbage collector manually. There are very few cases where you need to call it yourself. And what does garbage collector work with? It works with memory allocated on the heap, so with reference types or some other types that end up on the heap, but mostly reference types. And basically it collects an object. Object will be collected by garbage collector when it's no longer referenced by anything. So when it goes out of scope and when nothing else no longer reference it, then it will be garbage collected. So you create objects, they take space, they leave gaps because when we allocate memory, and malloc stands for memory allocation. So when we allocate memory, we don't take exact amount of space in RAM. We occupy a certain sector, a certain range in memory. And when, let's say this object A, needs this much memory, but the RAM sector it occupies is this big. So when we create this big object, we leave this small gap. Well, the gap is way smaller than this, actually. It just happens over time that we freed up this object. So there is a gap that is now free, that something can take place to it, but it's a gap nevertheless. And if we want to be able to allocate bigger objects or more objects, we just need to remove those gaps altogether. And garbage collector does exactly that. It collects those dead objects and it removes those small gaps, just compacting the memory, making it more usable, leaving less empty spots. And people say about iDisposable. iDisposable is used for unmanaged resources, so resources that are not really affected by memory. And those resources could be, let's say, a connection, and a file handle that is left open and not closed. Those are unmanaged resources. And memory is just RAM. And so we have an application and has those gaps, and you might ask yourself, okay, what if garbage collector didn't collect them? When will they be freed? When will they be removed? When will the defragmentation happen? And the answer is also when you close your application. If there are many gaps, if you just close the application, those gaps will be removed by the OS probably. Thanks for your explanation, Cray. I'll read it out loud. Basically, the garbage collector is moving around the chunks of allocated memory to try to reduce the gaps as much as possible because you want as little gaps as possible so there's continuous block of free memory. As raw coding said, if your object is 10 bytes big and you only have gaps of 9 bytes left, the memory is so fragmented you can't fit the 10 bytes object anywhere. That is a very good point. Thank you for the explanation. Now that we know what memory is, how it gets managed in C# and other managed languages, and what garbage collector does, let's move on to a wild zone called unsafe code. First off, unsafe code is something that you shouldn't be doing on a normal basis, and by default it's disabled, and you need to enable it in your project. For every project, you need to add this line, allow unsafe blocks, and set it to true. And why is it so bad or so risky to use unsafe code? Well, it's a Pandora box. It's a powerful tool because by circumventing the language restrictions, basically unsafe code is something that doesn't belong to CLR, common language runtime, that no longer is managed by garbage collector. And so it's a wild zone, and you need to manage all those things that are unmanaged by yourself. And you need to be careful. What happens if you mess up? What happens if, let's say, you have something that let's say goes outside of bounds, if array has index out of range and similar error happens? Well, an error won't happen. It'll just corrupt your memory. And therefore, unsafe code is very risky. It leaks memory. Anyways, to put in a nutshell, unsafe code allows two things: pointers in C# and fixed buffers, fixed arrays. Unsafe code indeed makes C# a lot like C++, both in terms of what you can do and in terms of speed. So first, let's talk about pointers. Pointer and reference type are very similar. The difference is that a reference type points to an object that is stored on a heap, and a pointer points to a physical location of memory. And pointers are static. So when you're using pointers with unsafe code, you need to make them fixed, that they don't shift, that their position is stable. So when you use a pointer, for example, if we have an array like this, it's a reference type. So A points to a reference to this array. And by saying int pointer P equals reference A, it basically says that this pointer points to a reference to this array. What does this mean? That this pointer points to the first element in this array, 10. The reference, the start of reference, the reference is the start of array. So here we have pointer 2, and this is needed. This is a fixed pointer, so it doesn't change. We cannot do anything with this P. But if you want to change something, like if we want to iterate through elements of this pointer, this array, through a pointer, we need a new pointer. So our new pointer points to the previous pointer, but by modifying this pointer, we don't affect this pointer. So by modifying P2, we don't affect P. If I write P2, it prints the first element in the array. If I increment the pointer, Fixed in P. What's the difference if we don't add end? Oh, okay. Okay. That's right. All right. Are you sure that we can do that because it's fixed? Well, we can try it. Let's see. So basically, by incrementing this pointer value, we can access different elements in an array. And basically, if we want to iterate through the array, we just increment the pointer. In live coding part, I'll try to demonstrate this in more detail. Fixed is another thing that is enabled by unsafe code. I'm incrementing by 1, but it actually increments by 4 bytes, as far as I know. The explanation for this behavior will be given after the lesson. I'll actually give a link. I took this from MSDN. Anyways, there is fixed. Fixed is used for a array that has a fixed size. So you don't initialize this array, you just assign it to compile time constant, and it will always be this size. So fixed buffer char array will be the size of a buffer size, always. Now, what are the benefits of fixed? It stays on the stack, so it's not really a reference type. It stays on the stack, and it also doesn't get called by garbage collector, and because it stays on the stack. The benefits of that is that well, garbage collector won't collect it. That's the benefit. Problems of fixed is that since garbage collector doesn't collect it, it causes fragmentation, and therefore you shouldn't abuse it. Yeah, GC cares only about the heap. So if you abuse fixed, you will have lots of fragmented places, so you need to be careful. Again, I'll do more demos after. I'll just want to go quickly through the material. So next is preprocessor directives. It's quite simple. Preprocessor directives are used for conditional compiling. It literally means that if I add a directive like this and it always starts with a hashtag, it will only be done if certain condition is met. In this case, if environment is debug, it will print this line in the console. And what I can put in instead of debug, I can put a .NET version, I can put debug, I can put some debugging symbol as well. So those are the things that I can put there. And what else can I do with preprocessor directives? I can ignore warnings, for example. Region and end region is something else. It's just a way of organizing code. So JS Striker talks about regions. I can quickly show. Basically this thing, the only benefit is that you can expand it collapse it if you want. Personally, I find it useful for code that is maybe you're lazy, you don't have much time to better structure code, and you still want to organize it quickly, then region is good. But I lean to aluminum that region is a code smell. If you want to do it properly, it will just extract code into a different place. Let's continue. Last part is reflection. So we already know that we can get information about types from reflection. We can get properties, attributes, as we talked about making custom attributes. But you can even call private methods with collection. So here I basically say, so we have a class dummy private. This class is very simple. It just has an ID and 3 methods. It has a static method called foo. It has non-static method called bar, and it has a foo bar method, which is also non-static, which takes a single argument. And then the string implementation of this is just printing the ID. The thing about this class that all those methods, foo bar and foo bar, are private. So private methods not used anywhere in the class. How do we call them from the outside? And disclaimer, in 99% of cases, you don't need to do this. And if you do need to do this, you should think of a better way. Reflection is the last resort when there are no other options. Here, we have a object, dummy, that is an instance of dummy private. If we get a type, from that type, we can also get a method. If we add flags that this method is non-public and static, we basically get foo method by name. And if we get method info, we can invoke that method from the object. Actually, object is not needed in this case, and with parameters, and there are no parameters in this case. So this basically calls foo method. Another thing that we can do with reflection, other than getting type info, is creating objects. So we can create objects in 2 ways, using Activator, which is bad. It can work on runtime, yes. So here we have dummy object, and here we create an instance of it using a parameterless constructor. So literally just creates that without taking any any parameters through generics. Very simple. And option B is to pass parameters, but then you need to pass a type as well. So that's a way to do it, to create objects using reflection, but this is extremely slow and not very practical. If you do want to make it more practical and roughly 10 times faster, you should use something that we already kind of learned, which is Lambda expressions. So in order to fast create objects using reflection, you should use compiled Lambda expressions. So why do we need expression trees? For this reason as well. We can basically take a type of dummy, of the object we want to create. We can get its constructor from the type. So we have now constructor, and we can create an expression for creating a type, a constructor. For creating dummy type instances. And the whole point here is that we compile this expression basically into a delegate so that it's actually a proper code. Just put an expression into a delegate. And this is way faster than Activator. Tens of times faster. And now if I invoke my delegate, I'll get the object that I want. Now some things. Questions. I couldn't really find Lambda expressions in previous lessons. When was this discussed in detail? It wasn't discussed in detail. Lambda expressions are basically delegates. When we talked about LINQ, that's Lambda expressions. And expression trees are Lambda expressions, but we can combo them and put them into a tree structure. That's the difference. If you look at MSDN, you'll see a Lambda section mentioning both LINQ, delegates, and expression trees. Yeah, this is literally a glue lesson, and all that I said, you're not really required to know, but I must put it before wrapping up C# chapter, because I want to be thorough and mention literally all that there is. Yeah, you'll learn about Lambda expressions, Lambda in general when you study LINQ in more detail. 2 lessons for it was dedicated, so definitely some time to learn and reflect upon yourself like people said. Now let's move on to live coding part, to some cool examples. And let's start with deconstruction. So you already saw we have this order class. But before we move on, please let me know if you understood everything. And I would really appreciate if you could tell me one thing that you think you understood very well and one thing that you would like to understand better or have a question. So something that you understood and something that you would like to understand better or are curious about, and I'll try to explain, or some seniors here will try to explain and help me. And I'll be right back in 1 minute. So please say that one thing. Okay, now questions. Donald said, when will you do lesson on using COM libraries from C#? That lesson will never happen, I'm sorry. Dave94 said, dynamic LINQ went past me, but I really liked the memory allocation and unsafe stuff. Nice. Catgirl said, does unsafe have things like malloc too? Yes, it does. Similar stack alloc. Okay. Okay, let's move on with live coding parts. So I made a bunch of examples for every piece of code that we demoed. So first, deconstruction. If we look at this demo, the basic one first is datetime. So you literally just have Let me make this good. So you literally just have a string. You pass a string into try parse, and you don't care about the datetime result. All you want to know if the date was parsed successfully or not, if this string was a date or not. And here's what you can do. Just pass and use discard operator to ignore the output of try parse. The result is ignored. Just datetime is taken, is data. Another thing, remember the example with the order. So we create an order, and here we can ignore the three things that the order returns. We can ignore its name. We can ignore its what was it? We can ignore its description, and then we can ignore its line scout. We only take the name. So here you have it. We print an order and its name, ignoring the other two things. And here we print an order with name, description, and lines count. So if I go and run the examples, deconstruction, didn't use that one. Run. Okay. So if we run the examples, you can see that it's as expected. And one more thing about tuples, it's quite interesting to see that they actually get printed with brackets. That's the default implementation. They implement the string by themselves. So for example, if I create a tuple 5 and test, it prints 5 and test. If I return, well, 1 and test is the things that I printed in the last one. And the second one was demo values return. Oh, yeah. In here, I also printed this one that was created. So it also, well, it doesn't print the names of properties. It just prints the values like that. All right, let's move on. So I just demoed tuples and deconstruction. Let's move on to unsafe code. For unsafe code example, I made something that is crazy, so a mutable string. As we know, under the hood, a string is a characters array, but not really, because that array is immutable. So I also made a characters array that is mutable, that is of fixed size, and therefore I call this class struct short mutable string. Short because it's only 128 characters long. So short mutable string is a string that can be treated as a mutable string. We don't need this. And here I put the stuff that we already know. So we can modify the string through an indexer. So we pass an index and we can change the value of a string at that index. Or we can get the value of that string at that index. We can also directly assign the string into an actual string or from an actual string. And we create this string from a string. And the key point of this string is that we can basically do modifications by index without nearly any overhead. It happens immediately. Yes, implicit and explicit are casts. I'll show the example soon. So, right. Benchmark demo. So basically, string, short string. I can assign a string into short string because I use the implicit operator. I use implicit operator, and it means if I pass a string, it automatically builds a struct out of it. So if I pass it a string, I can store it into short mutable string. Or if I pass this into a string, it will basically convert it back into a string. So here I basically demoed. Let's make it more interesting. Let's say we have a misspelled allo unsafe code and we want to say hello. And I can do that with this. So if I run this code, you can see that I managed to access this string and change value at index. A character at index 0 is now H. You might ask, what's the point? Why can't I just use a string? Well, if you wanted to do the same with string, we can go into benchmarks and see basically some operations that you would do in one way or the other. So, for example, if I want to replace a character at position 10 with my code, all it would take is to create short mutable string and say that character 10 is C, for example. And if I wanted to do the same with a string, the optimal way would be to create a string builder, remove character at position 10, and insert the character that we want to replace position 10 with at position 10. So this is what we would do with string, normal string, and this is what we would do with unsafe string. And we can run the benchmarks. I use benchmark.net for it, and if we run it, let's see what happens. I need to run it in release mode. So let's wait a minute or two. And in the meanwhile, let's look at the code. The benchmarks. So first example is replacing character at a given position, at a given index. And second example is capitalizing character, first character, basically Pascal casing. So if I had to do this with a string, I would first need to take the first character, convert it to upper, substring from first position all the way to the end, and add the first character with the string, and that's the result. Slow down, don't scroll so much. The image is all fucked because it's the low bitrate. Sorry. Donut X3 asked, But what about system create method, system string create method? What about it? I honestly never use it. How is it different from constructor, string constructor? How is it breaking boundaries? Let's see. State creates a new string with specific length initialized after creation by using specified callback. So it modifies the string right after initialization. Okay, I never used this method. But I presume that I could implement my methods with this. I imagine if I wanted to do something like I did here, it could be more optimal with this method. Yeah. Okay. What about tstate? What is tstate? It's really cool, but what is tstate? Tstate. That's nice. Anyways, I think we have the results. So the key points here from the benchmark is I don't know. Anyways, the key points from the benchmark is that if we look at capitalization thing, which one was first? Capitalization. So capitalization, we just took character and we converted to upper. And we took substring of the string. So this does probably very little allocation. And this isn't, these two lines are not as expensive as these lines, even though we used unsafe code. So our code is actually slower. But if we look at modifying string at a specific place, the way we did with string builder as opposed to the way we did with mutable string, it's a few times faster. But as Donald said, apparently there is that method as a parameter. Okay. Let's try to do this because let's try to do this in the string create method as well. So optimal method. String create. Length creates a new string, the length of a string to create. So it will be the same length as the text. State. What about state? Random object. Let's just put null then. Span action. What is span action? As the data for the string. Okay. Text. Oh, I see, I get it. Okay. Span action. Let's create a method. So it's an action. We take a span. At position 10, we want it to be C. So does this mean that we need to save it to the argument? No. I need to convert the argument into span, right? And then change the span. Not sure how this goes. There's nothing else. Okay. With a specific length initialized after creation by using the specified callback. State. The element to pass to action. A callback to initialize a string. I get that. So I need to convert the state. Let's see the example. Nice, no examples. Okay. I see. Span is and span at 10, let's say, is that. Let's see. Using system create. I did copy the whole string to the span. Yeah. Okay. Thanks for the hints. Let's check if this works. Span. I'll put this to program because it's unrelated to anything. Span string create demo.